Today's lesson will describe electrolytic cells and how they differ from voltaic cells. Electrolysis is a process that uses electrical energy to create chemical energy. This electrical energy comes in the form of a flow of electrons from a battery or another power source. Because electrolysis requires energy, it is technically an endothermic reaction. Electrolytic cells use this process of electrolysis. The most important thing to understand about electrolytic cells is that you should get a negative number when you calculate the net potential energy for the cell. Because the number is negative, the reaction is not spontaneous. To get the reaction to go, a source of electrical energy is required. In electrolytic cells, the cathode is negative and the anode is positive. This is the reverse of the charges of the electrodes in voltaic cells. Here is an example of an electrolytic cell. It has two lead electrodes dipped into a solution of zinc sulfate. According to the chart here, you can see that the strongest oxidizing agent is below the strongest reducing agent. This means that without the addition of electrical energy, the reaction would be non-spontaneous. If you were to calculate the standard cell potential for this example, you should get a negative number. This is further proof that the reaction is non-spontaneous. Since this reaction requires power, it might not seem very useful. It is actually a common procedure in industry, though. If we want to force a reaction to occur, sometimes we can supply electrical energy. This process is most often used to produce elements. An electrolytic cell looks different from a voltaic cell. It still has two electrodes, but it only has one electrolyte, and it requires a battery or power source. The power supply acts as an electron pump. The push of electrons into the electrolytic cell will drive the reaction. On the previous slide, I mentioned that the electrolytic cell only has one electrolyte. Why don't we use two and keep the two half cells separate? The answer has to do with the spontaneity of the reaction. We need to keep the two half cells separate in voltaic cells because the entities would all react without sending electrons through the wire. In an electrolytic cell, it is not important to separate the oxidizing agent and reducing agent because they would not react spontaneously. This table from your textbook summarizes the similarities and differences between voltaic and electrolytic cells. The similarities include that the electrons still move from anode to cathode, and anions move to the anode, and cations move to the cathode. The differences have to do with the spontaneity of the reaction and the cell potential. A voltaic cell's cathode is positive, while the cathode in an electrolytic cell is negative. A voltaic cell's anode is a negative electrode, while the anode in an electrolytic cell is positive. The process for analyzing electrolytic cells is very similar to the process for analyzing voltaic cells. You will need to identify the strongest oxidizing agent and strongest reducing agent, and write the half reactions. Once the electrons are balanced, write the net cell reaction and calculate the cell potential. If the question requires, you may need to determine the minimum voltage required to force the reaction to occur and draw a diagram. This example shows the steps required to figure out the minimum voltage for electrolysis of lead-2 nitrate. The strongest oxidizing agent and strongest reducing agent are identified, and the net reaction and standard cell potential is determined. The standard cell potential is negative 1.36 volts. So the minimum voltage for the electrolysis of lead-2 nitrate is 1.36 volts. Here is a diagram of an electrolytic cell. Electrons will still flow from the anode to the cathode, and the anions will travel towards the anode, and cations will travel toward the cathode. Please complete the October 24th quiz.